welcome. Thank you everyone for joining today's webinar brought to you by Codefresh Live. Today we're presenting Automatic Deployments Relieve Pain and Suffering from Vivint. Our presenters today are Ben Mathews and Jared Meeker from Vivint. And Ben and Jared are going to relive their past deployment pains and show you how Vivint transformed their build pipeline and improved their deployment times from 3 to 4 hours to just 5 minutes, amongst many other things. We have a great presentation for you, but first, a couple housekeeping notes. We encourage your questions throughout the session. Just please put them into the Q&A box on your Zoom toolbar. This helps us keep much better track of them than in the chat. We want to make sure and not miss your questions. But please feel free and use the chat as needed. Just for specific questions, add them to that Q&A bar. This session is being recorded, and a link to the recording will be sent to you by tomorrow from me, Taryn at Codefresh, so look out for that email. Lastly, please remember to check out codefresh.io/events for our upcoming webinars, as we have fresh and informative webinars for you several times a month. We even have one coming up this Thursday. So with that, I will hand it over to Ben to kick off the presentation. Hi, Ben.
Hello, everyone. Thanks for joining in. I hope we have something informative for you. We're going to talk about automatic deployments. That's what everyone wants, and how they relieve pain and suffering. So specifically, we're going to talk about my company, Vivint's deployment migration that we ended up on Kubernetes, Helm, Homefile, and Codefresh. I am Ben Mathews. I am a software engineer. I love to play with all of the latest CNCF toys.
And I am Jared Meeker. Been at Vivint for a while, love everything ops, and real excited to be here.
So Vivint as a business is a publicly traded company. They are a leading smart home company in North America. We provide an integrated smart home system with security monitoring for more than 1.5 million customers and growing rapidly. It's a nice problem to have on the tech side. Technically, we have 100 plus Kubernetes nodes on 4 clusters, 4,700 deployments, daemon sets, stateful sets, and cron jobs, over 8,000 pods. Our customers' homes are wired and send us messages about 1.5 billion a day. We peak out at around 25,000 messages per second. The customers have a mobile app that they use to monitor and control their home, and we get about 5,000 messages a second from that. We deploy multiple times a week. So going back a couple of years to 2017, we had our software installed on 40 virtual machines. We had a salt configuration for them, but used it badly and rarely. Deployment was a completely manual process. We deployed weekly and thought that was a major improvement from the former every month or so deployment. Deployment consisted of draining nodes, manually moving traffic around on our F5 load balancer. We often did hot patching. In the pets versus cattle analogy, we had a lot of poorly behaved pets. Even when things went well, we tolerated minor service disruptions. We were so unconfident that we could deploy that any developer who had code in the release was required to be sitting in the area next to the operations guys during the release period. So we knew we had to get better, and we looked around and saw Kubernetes. It was first released in 2015. It was still pretty raw at that point, but it seemed to fit what we needed. Jared figured out how to install and maintain a Kubernetes cluster. I figured out how to use Kubernetes. Because it was so new, we had a lot of adventures with bleeding edge kernel requirements, broken network drivers, obscure configuration issues. We also had to modify our software quite a bit along the way to break all the hard-coded paths and other assumptions, and to harden our code to run in a cloud environment. By January 2018, we had migrated the first part of our production workload to Kubernetes, and we finished that migration by early 2019. And this was worlds better than the previous, where our deployments went from 4 hours to under an hour. That was more reliable. We had the Kubernetes scheduling, so we didn't have nodes that were running too hot and nodes that were under allocated. Kubernetes restarted failed processes. We had resource caps, all the other great Kubernetes stuff. But as we deployed all those workloads, I wrote every single one of the Kubernetes objects manually by hand. They were all hand done. And so deployment meant that we did a kubectl edit and type changes. And sometimes we typed the wrong image tag. Sometimes developers would add new parameters or whatever, and that wouldn't get communicated. And so we had outages still. It was better, but we still had outages. And as we got to appreciate and feel comfortable with the production Kubernetes, we wanted to do the same thing with our beta and development environments. And we knew that the challenges of maintaining one environment's worth of handcrafted YAML would be impossible to scale to multiple environments. And so we wanted something better. We knew that we needed configuration as code. That's where, instead of manually typing things, you have the configuration in version control where you can branch and do pull requests and so forth. We wanted to have some kind of templating ability where we could abstract out the common bits between our different environments. And so we looked around. We found at least 3 options that appeared to meet our needs. Fortunately, we picked what ended up as the industry winner in Helm, and it did meet our needs. It had a templating language from Golang. It was well supported, and it solved all of our problems. There were some additional things that we had to work through to use Helm properly, but it is and continues to be a big part of our deployment solution. Also, because of Helm's wide adoption, there are corporate and community built charts for just about every public piece of software. So they aren't always perfect, but at the least they serve as a great starting point, so you don't have to start from scratch. So over the course of 2018 and 2019, we wrote Helm charts that were initially used in our dev environment. Using these charts, we created a platform as a service that any developer or tester could create a replica of production with any branch of code in minutes. And by late 2019, we had converted all the handwritten YAML in production to be deployed with these Helm charts. And this again was a major improvement. We took the deployment time down to half an hour, and again had a major step up in our reliability. So this screenshot on the right is from our wiki page at that time, which had a number of commands, well, probably 40 commands on how to do a Helm upgrade for each specific chart. And so it was still a manual step where operations was going in and typing things, and that meant that there was still mistakes. And a mostly automated process means that you can break production quickly and completely. We once deployed to production with the beta configuration, and you can guess that didn't go very well. This step in the process also had a manual workflow, which meant that we were communicating the changes via wiki pages and Slack, and that again resulted in miscommunications, mistakes, and outages. And even though we'd gone from 4 hours to half an hour, people still thought it was too slow. And I assume this too slow complaint will continue forever because people always see that it could be better. And so at this point, we knew we needed some kind of automation. So I identified 40 plus different continuous deployment products and identified some criteria. We wanted to be able to use our existing Helm charts. We wanted to continue to do our continuous integration with Jenkins. We wanted logging and auditing. We wanted to use our Okta and Bitbucket server that we already had. We wanted this GitOps style, and we wanted it to be easy to use. And of those 40 products, there was only 3 that met our criteria. There was some good products that didn't use Okta or Bitbucket, but only 3 that did all of these. And this was 2 open source products, Argo CD, Flux CD, and Codefresh. And in the 9 months or so since then, Argo and Flux have combined forces. So these are the 2 that we were really considering. As we were working with Codefresh on our integration, they suggested Helmfile to meet our GitOps requirements. It encapsulates all those commands from our wiki page into an easy to read YAML configuration. And if you look at Helmfile, you'll see that it is alpha status. It doesn't have a whole lot of adoption. There's no fancy website and marketing team, but it works really well. And it closed the configuration as code loop that we were trying to get rid of, to get to. And when we discovered it, I wrote a script that pulled in our existing configuration and had the whole workflow working within a couple days. The hardest part was training our QA staff to drive our release process. And if you're using Helm, you absolutely should be using Helmfile. It just made Helm so much easier to use. So what the workflow that we ended up with is visualized there on the right. We created a Helmfile Git repo that contain that configuration, and each week we create a release branch, and when a commit is made to that, a webhook launches in Bitbucket, and then Bitbucket will do a Helmfile apply to our beta environment. There is a manual QA approval step, and once that is approved, then Helmfile diff is run. And that shows the differences between what's currently running in production and what would potentially be released. There is a manual ops approval step, and then a Helmfile apply, which syncs those changes out to our production environment, and a Helmfile test. So let's take a quick detour and actually look at what that looks like in the Codefresh YAML. So the first step is cloning from our Git repo. The second
You can
step,
zoom in just a tiny bit on that, Ben. It's a little bit small.
Sure.
Thank you.
Does that look better?
Perfect.
I'll do one more step. The second step is the deploy to beta, and you see it says freestyle there. That basically means we can do whatever we want. There is a number of prepackaged steps, but we wanted some of our own functionality. So we say we're going to run with the Helmfile image, and the CI helm.sh is a script that is checked out from the in the above step. And so we run a couple commands. The apply that I mentioned before syncs those changes out to the beta environment, and then we run the Helmfile test, and we pass in some environmental variables that direct it to the right place. We send out a Slack message that was done, so that people aren't having to monitor the Codefresh website or receive the emails. And then here's the manual approval step. The pending approval is one of those prepackaged steps. So in the Codefresh user interface, there's just a button that somebody that has authorization to presses. And at this point, we branch off. We have 2 data centers, so we go run the same thing basically in the east and the west data center, and that launches. Oh, and I see that I didn't quite clean that up. So here's what the east looks like. Again, we are checking out the Git repository, and here's the diff step. Again, it's a freestyle step in the Helm file image, and here's the command that we're running, and the results go to standard output. They're visible in the Codefresh UI, and so somebody in the ops group will go in and look at that, make sure that it meets the eye test, and once they click approve, we send this message to a Slack channel so that everybody knows that the deployment's going out, and we do the Helm file apply. We send another Slack message saying that we're done, and then finally we run a Helm file test. So it's all pretty simple and easy to read. So by late 2019, we had Codefresh, Helm, and Helm file all integrated, working well. We had a good workflow in our organization. Deploys were down to about 5 minutes and more reliable than ever before. We had nice Slack notifications. Everyone appreciated those. But as time went along, we noticed there was some reoccurring problems that would bite us during deploys. They weren't really deployment issues. They could have and should have been caught earlier if anyone was paying attention. Some of the first things we ran into were specifying images from our development Docker repo, which isn't accessible in production. So when somebody did that, we would get image pullback offs and outages. We also had problems with people using deprecated Kubernetes APIs. And really asking humans to be perfect in code reviews is hard. So we decided to try to automate that. We looked at linting tools, found that they would catch general problems such as running as root, using the default namespace, not setting resource requirements, but found that they were all too raw. They didn't let us turn off requirements we disagreed with or weren't ready to enforce. They didn't let us add new business specific rules. And so that led us to Open Policy Agent. It's so flexible and so powerful. Really, we're using a cannon to kill flies. So these examples aren't in any way showing its limits. We currently enforce policies at 2 places. We run some checks when we package the charts, and then when people make changes to the Helm file configuration, we template out what all of the YAML would look like when the production configuration is applied to the charts. And so we check for deprecated Kubernetes APIs, a liveness probe, which checks that the software is still running as intended. We had a problem with our Prometheus annotations, where it's supposed to be on the pod, and substantially more than once, people would put the annotation on the deployment, which meant even though metrics were being produced, they weren't being scraped and so weren't available. We checked that images are not tagged as the latest, that they're not from our dev Docker registry, that a CPU request was being set. Horizontal pod autoscaler minimum was less than 3. By policy, we always have 3 or more for high availability. And then in our development environments, we have a set of well-known passwords just for convenience. And if we find those in the production templated YAML, we know that somebody has done something wrong. So we're checking for some of those. So I'm really excited by the changes we've made. In 2.5 years, we went from really barely hanging together on deployments to a pretty good situation. There's still some things we're looking to do in the future. We're still not fast enough, and there's not enough visibility if a deployment succeeded. So we're working on those. Specifically on the reliability front, Kubernetes deployments have liveness and readiness probes that detect when a pod isn't working or doesn't have available dependencies and take appropriate action. And Helm tests are post-deploy tests that verify the correctness of the deployment. We've implemented these in some of our deployments and are working to get them finished everywhere. And once they're on in all the deployments, we can be sure that if a Helm deployment finishes, that it's working. And so with this, I'll turn the remainder of the presentation over to Jared. What I've talked about is the ideal world in pre-production where most everything worked, and he's going to talk about the operations where things don't always work perfectly.
Great, thanks, Ben. Give us a minute to switch. Who's sharing their screen? Does that look okay?
I see you.
Good.
Great. So thanks, Ben, for covering that. We've made some great leaps and bounds in our deployment processes. And so I'm going to take a few minutes. We'll talk about the operations side. But I want to cover a few important bullet points first. One is that anyone that's worked with Kubernetes and our Helm knows that just because you run some commands doesn't mean what you want to happen actually happens. So a few things that I always keep in mind, and I'm reminded of this continually anyway, but bugs are inevitable. They're going to be found in the tools that we use. They're going to be found in the software we write. So we need to expect things to break. And that allows us to react faster when things do. So we also need to know our environment and the tools available. Initially, when we started Kubernetes, we didn't just want to blindly run a cluster that was started by some magic script, because when things go wrong, we need to know how to fix it. So we worked through the process of actually figuring out how to run the cluster ourselves so that we knew all the ins and outs of how all the different pieces worked. And it has proven to be very, very useful. And then finally, no matter how much care and attention we give to computers, they are going to make our lives miserable. And that's just a fact of life. So some of the most common problems that we see today in our deployments are based around our Helm charts. So sometimes Helm charts are written and they're incomplete, or they're not set to run at a production scale. Sometimes they just have flat out wrong values. We have, different branches for different environments, and sometimes those don't get translated over the same. Other things we run into, of course, are software bugs. We do run into things that we test in our test environments. They run great. We deploy into production and they tip over completely. So we do expect to see that on new deployments and try to anticipate that moving forward. Also, sometimes Kubernetes itself is broken. It's been pretty stable in the last couple of years, and it seems to be moving more so in that direction, but we can't take anything for granted. In our post-deployment arena, we have a lot of automated things. Helm, as we saw in our deployment pipeline, runs Helm test at the end to make sure that a lot of the object properties we wanted set in our cluster, like, for instance, environment variables and image tags and things like that, that what we told Helm to deploy actually made it out. We also have a lot of internal tooling and automated tests to verify that once we deploy, things are still working, the features we wanted are out, and that we didn't break anything. And then, of course, one of our most key aspects to our deployments is our monitoring and alerting. We rely on that very heavily to know if certain things break, and so we can react quickly to get those fixed. Also, in our post-deployment environment, we have manual things. Sometimes we don't feel like we need to run these, but they exist. And in some cases, especially when we deploy something new, we do want to check these and make sure that we're A-OK. One is we can check a rollout status. When you deploy something in Kubernetes, it starts to roll out pods. Either those pods are new because the deployment's new, or those pods could be replacing old pods with the new pods that are running the new code. And so the rollout status will tell you how far along that process the rollout is. And that's really key, because a lot of times if there's a bug in the code or some other thing is wrong with the deployment, your rollout can actually pause. You'll get 1 or 2 pods out there, and then when Kubernetes notices that those pods can't keep running or they're not healthy, it will actually stop rolling things out, which is really useful. But you can't just assume that because you deploy something, it worked. So rollout status is key. Also, the kube control get deployments is really useful to look at, make sure that we have all of our pods are up to date and available. We also have some internal tooling manual tests. We have a lot of physical devices we put in our customers' homes, and we're constantly working on doing automated tooling around those. So that's a work in progress. So what happens when things go bad? Because we know they will, and especially in the Kubernetes environment, there is a lot of complex things happening. You've got IP tables, rules, and 20 different pieces of software all trying to, make sure that what you want running is running, and that they get restarted if they crash and things like that. And so deploying our own software into that environment makes it even more complex, and it doesn't always go as smooth as we'd like. So we're going to talk about some tools that we look at when troubleshooting our Kubernetes deployments. The first thing I want to mention is Blue Matador. So Blue Matador is one of our tools that we use to monitor our Kubernetes cluster and our Kubernetes nodes. So Blue Matador is great for quite a few reasons. One is it understands AWS and Kubernetes as native objects. It knows the ins and outs of these two environments, and has a lot of predefined rules that allow us to detect when things are wrong without us having to go find what those might be and then set up the alerting around them. It's distributed, so each node gets its own agent, and that allows it to be performant and responsive when things go bad. You can deploy it standalone, so outside a Kubernetes environment, or if you want to deploy inside Kubernetes, you can deploy daemon set, and that'll run on every node. It integrates with most of the most popular notification services, and it's got a really useful web interface. One example of that interface is the dashboard. So this isn't our dashboard, but it is an example of one, and you can see you've got some basic time graphs of alerts over time, whether they're anomalies or warnings or alerts. You can see the frequency of events. On the right side, you see a list of those events, and those are all clickable. You can drill down into each of those and see all the detail about what the deployment is and what the alert was about, and when it happened, and did it happen to multiple pods in that same deployment, for example. It does refresh nearly near real time, and as I said, it's very extensive and allows you to drill down and see what's going on. The events specifically are super useful. These are what are used to fire off the alerts. You can search for events. You can drill down to each one individually. There's a timeline view. You can see if you want to see if there was an increase in events over a certain time. And you can see the node thing was running on, the deployment, the name of the pod, what the errors were. In some cases, you can see here the high pod CPU. If you set limits on your pods, which in a lot of cases can be really useful, it can even tell you when you start reaching some of those limits. So you don't have to sit there and run command line tools all the time to see what's happening. So it's really, really useful that way. In Kubernetes, one nice thing is everything in Kubernetes is native in Blue Matador as well. So it understands cron jobs and daemon sets and deployments, replica sets, and services. All that is listed and monitored and watched over, so you can troubleshoot and get alerts on things. In addition to Blue Matador, we also leverage Prometheus very heavily. It is probably the de facto standard for Kubernetes these days in monitoring not only the cluster, but pretty much any other thing you want to monitor. It's really extensive. And so we use it for monitoring our nodes. We use it for monitoring Kubernetes itself. We have used it in our application to get code statistics out of different metrics within our code. And of course, there's an exporter for just about every product under the sun you can think of, whether it's load balancers or databases or caches like Redis or Memcache. There's all sorts of things out there that plug into Prometheus that you can scrape data from. And then, of course, it has a companion app or a program called Alert Manager. And we do leverage that so that given our set Prometheus queries on the things that we want to watch, we can get alerted if those change, if they get out of spec. The nice thing about Prometheus for us is we've been able to, because it's so extensible and flexible, we've been able to consolidate all of our metrics into one place. So when we want to, say, build dashboards or get alerts on things or pull in additional information when we have an outage or are suffering performance issues, it's a one-stop shop, excuse me, for all of our data. And it's real easy to pull that out and view things side by side and make some tooling around that so that it's real easy to query. We also leverage Slack quite heavily. We don't just use it for collaboration. We have several bots that talk to us in Slack. One bot I'll refer to as bot 1 can actually query Prometheus data and generate graphs and display that in our Slack channels. That's really, really useful when we're firefighting. We want to query and say, hey, show me this or show me that. And we can pull that into our discussion and see those real time. We also have another bot, which I'll call bot 2, which actually listens for incoming alerts, whether they're from Blue Matador or Alert Manager. And it can actually ask bot 1 to pull in relevant graphs. So those two bots in particular have been really useful in allowing us to have something at our fingertips when we get a page and we need to pull up our laptop and hop into Slack and see what's going on. We have a whole lot of context around what's happening, and we can easily request more. So those have been really invaluable as well. In addition to those tools, we use the Upstack and Grafana to build dashboards, look at logs. We save our host logs, we save our pod logs, we save our application logs. Everything we can save, we try to. Within reason. There is definitely a delicate balance between logging too much and logging what is useful, and that's always a constant battle that we're fighting. But we do leverage this quite heavily in going back and looking at things as they're happening or as they've happened. Great tools for things like postmortems, things like that. In addition to the nice graphical utilities and the automatic alerts, there are several command line tools that we use to really dig deep sometime and see what's going on and maybe even find the root cause of some of our problems. These might be familiar to you, but these are some of the most common ones, at least in our Kubernetes environment, that we leverage quite frequently. We describe deployments. We can look at the events as part of that output. So if a deployment has changes in pod counts or if it's been modified, we can see that in those events. We can look at services. One thing that we notice with services, if things aren't running, is we verify that they're the ports we expect them to be. And with the describe command, you also get a list of the endpoints, so the pods that service is connected to. So often labels get messed up and a service will not have any pods to send traffic to. And so it may have the right port and it may be defined, but the traffic's not going to get anywhere. We get pods. We can look for status of not running or restarts, things like that. That's useful in that output. One thing that we use quite a bit is the kube control top pod command. And if you haven't used that, what that allows you to do is you can add labels, you can add namespaces to this command to kind of refine what you're looking at, but you can see the CPU memory utilization of pods. And that's really nice to know, especially when you're setting different resource limits on your deployments, so that if a pod has, say, 200 megs of memory it can use. If you want to know how much it's actually using, you can hit a Prometheus to run some queries, or you can run the kubectl top pod and with the appropriate flags, and you can actually pull that up in your terminal at will. And that's really nice to see when things start to crash and get killed. You can see, was that a one-off or all the pods in that deployment having that same issue? Our top offender is typically Python code. It likes to pull in lots of dependencies. And so minor changes to some Python code could result in drastic increases in memory utilization. So, so that's really useful. And then, of course, you can always look at the pod logs themselves. Kube control logs is great for looking at a single pod log feed and see what's happening. You can tell in real time, or you can look, all the way back from the inception of the pod if it's available. However, it's not great when you want to look at multiple pods or all the pods in a deployment, per se, at the same time. And that's when we come to a tool called Stern. I don't know who found this at Vivint. It's an open source project. There's a link to it at the end of the slides. I've heard of some other tools that are quite similar. But because the Kubernetes API is so well defined, it's really easy to write tooling against it. And so this particular one will allow us to run a log tail against a large selection of pods all at the same time. It color codes outputs, so the pod names are colored and you can see which pods are logging and things like that. But it's a great way to watch logs for anomalies. An occasional request that comes through that throws an exception or something like that. And it's got some really great command line flags for cutting out or searching for particular strings in those logs. So we use Stern and like it a lot. Journal CTL is one of our final ones. When we get to troubleshooting our systems and we ruled out anything inside Kubernetes, it is inevitable that some of the problems will be caused by outside influences, whether it's a buggy network driver or other things on the system level itself. And so a few things that we tend to leverage, we don't use these very often because, for instance, the kubelet logs are extremely verbose and they're really hard to kind of filter through and determine, what's a real problem versus what's just normal behavior. But they do exist, and knowing these commands can be really good for troubleshooting things like Docker or kubelets or other system services we have. One interesting thing to note here is we have found that as we've scaled up our Kubernetes environments, that there are a lot of system tuning that need to happen to run a fairly large Kubernetes cluster. If you think about it, inside Kubernetes, you have pods, and each of those pods has an IP address. You have services, each of those services has an IP address. You have ports defined on your services. You've got sometimes pods that allow things like Prometheus scraping. You've got Kubernetes specific services running inside your cluster. And with 8,000 pods or so all running, and I can't remember how many services we had at the last count, that's a lot of IPs to track. And we found early on that as we were scaling our cluster, the default values in the Linux distribution we were running weren't allowing us to track all the connections we needed to. So we were seeing really weird things like some services just randomly couldn't talk to something else, or you would hit an API endpoint and the ingress just wouldn't work. And it was really hard to track down, and we actually found the pertinent messages in dmessage, and noticed that we were getting errors about neighbors and things like that. And that was indicating that our ARP cache was too small. So something to think about, when when you run a distributed environment is, we went from, hundreds of VMs to multiple Kubernetes clusters. And by doing so, we consolidated all that traffic and all those IPs and all those ports and things like that all into a smaller set of hosts that allows us to scale dynamically. And so some of these tuning parameters you're going to notice in Googling errors and stuff you see in things like dmessage and other system logging. So to recap, what we have is, as of a few years ago, we had really poorly tooled manual deployments. We tried to automate them. We had some tooling around that, but it was still a very, very manual process, and it didn't always work well, and was prone for user error, typos, just everything under the sun you could think of. Deployments took like 4 hours, and that's a long time to deploy, especially when you know that sometimes we deploy buggy code. And so if you deploy buggy code, it takes you 4 hours to deploy. Now you've got to create a fix, get it committed, get the packages built, and then redeploy. And you're looking at least another 4 hours. So one thing that we had to do is a lot of our hotfixes had to be manual file edits on each of our servers because it took so long to deploy that it just, oftentimes it wasn't an option to deploy, again, unless it was a massive, massive change. So, so we had lots of manual changes to get things running. Yes, we were in a monolith situation. And so when one thing broke, lots of things broke. When we couldn't deploy something, we couldn't deploy anything. And then even verification, like we had an environment where we had, you only wanted to run so many of each thing so you could handle a production load. But that was all a manual setup. And so we had to make sure that we had X number of this service running or X number of that service running. We needed to make sure that when we deployed code, the services actually started. And we didn't have any good automated alerting on our on system. We didn't have say Blue Matador to monitor our systems. And so we didn't really know when things were bad until we hit our peak load in the afternoons. And that would, all of a sudden, things would start behaving really poorly, and we'd have to go figure out why. So as far as the ops teams go, we were in a really bad place for these deployments because it was really hard to have a lot of confidence that we were deploying something useful that was not going to cause problems down the road. Now, with Codefresh and Blue Matador and Homefile and Kubernetes, we are nearly fully automated. We do have some stopgaps in place to help us ensure that A, we know that code is being released, and B, that it's the code we want. We have some, been mentioned in our Codefresh pipeline. Codefresh has a great UI that we're unable to show because we really only have it set up that can deploy production. And so we opted not to share that. But in the UI during our deployment pipelines, as it pauses different steps, we can actually go in and visually check. Now, we do miss things in that environment, and that's why we're leveraging things like some of these tools that Ben talked about where we can verify that our charts contain or don't contain certain things. But we can look and see if in the output of our diff between what we want to deploy and what's currently in production, that we don't delete major swaths of services and deployments without replacing them with something else. So we do have a kind of a quick visual check, and even that has caused some reflection on some of the things we're deploying and caused some discussion. But the nice thing is getting to that point is much faster, and having the tools around detecting that now give us so much more confidence that our deploys, once we're confident that we're deploying what we want, that it's going to work better. And that's been proven to be true. We have almost zero chance for user error. With our Helm chart problems aside, the actual deployment process is really straightforward, and very little hand editing happens at all for our deployments. It's really nice. We're able to deploy individual pieces instead of the whole thing. We're no longer deploying this one single huge monolith to everything at the same time. This has helped us iterate over bugs faster. This has helped us to deploy quicker because we don't have to role pods for things that we're not deploying. And Kubernetes and Homefile have really been key in allowing us to split some of those things out. As far as alerting goes, now that we've got tools like Blue Matador in place, we've got our Slack bots in place, we're able to find out very, very quickly when things go bad and respond faster and get more context around those. And that means less downtime for our customers. When you process 25 requests a second from all of our customer panels and things blow up really, really fast. And if people can't disarm their houses when they want to, or if they don't arm when they're supposed to when they leave their home, or they don't disarm properly when they come home and their panel goes off, those are all really bad scenarios for us and things that give our customers a bad taste in their mouth for our products. So we really try to keep things up and running. And a lot of these toolings that we've got in our code pipeline have really proven to be very, very useful in helping that customer experience. We can really solve hot fixes a whole lot faster. Oftentimes within 5 or 10 minutes, we can have a hotfix ready to go and through the approval process and being released. And of course, I already mentioned we have significant downtime in process alerting. So all in all, moving to Kubernetes and leveraging these deployment tools has been really, really nice. We can all sleep better at night knowing that our systems are running, that we get alerted when things go wrong. And we don't dread deployment days when one of us has to spend half a day trying to deploy something. So we're happy. And with that, I'll give a few links to some of the things that we've talked about, and I'll turn the time back over to Taryn.
Awesome. Thank you so much, Jared and Ben. We do have a few questions still to answer. A couple got answered already via text, but I have a couple questions for you from the audience. First, John's wondering if your tool chain would work with Teams rather than Slack, do you think?
Probably. We do use Teams a little bit, but it came after our adoption of Slack. And so really, if Teams has the infrastructure for adding things like bots and webhooks and things like that, there's no reason it wouldn't work. Slack has been nice because they've got some public libraries available and some code examples on how to leverage their APIs. And so if Teams is just as open, then there's no reason it wouldn't work there as well.
Sounds good. And he also asked, what about Jira interoperation?
We don't interoperate our things with Jira. We do have code reviews that are kicked off automatically and things like that, but that's all outside of our pipeline. For us, when we commit some changes to our Helm file repository, that's what triggers our build pipeline. And so everything with building things and doing code reviews and things like that are all beforehand.
So Jira does have a really rich set of REST endpoints that you can integrate with if you want. Like Jared said, the workflow that we've defined, we haven't had the reason to do that. But if you want to create a workflow that involves Jira where you're automatically opening and closing or amending tickets, then absolutely you could do that.
Awesome, thank you. And our next question, are you using EKS or self-managing Kubernetes cluster?
Our Kubernetes clusters right now are just about all on-prem, so we manage our own clusters.
Jared, you got to elaborate and brag about your system a little bit.
There's not a lot to it. We do have plans to look at being able to burst into the cloud for things like major events throughout the year. Our biggest day right now is Halloween. We have a lot of doors opening and closing. A lot of our customers have security systems and use door sensors and things like that. We have video doorbells that detect motion and record clips, and so Halloween is a really, really, really big day for us, and we prepare a couple months ahead to try to anticipate what that load's going to look like and get things ready. So It would be nice if we had a little automatic bursting when things got really, really busy. But we also try to be very, very performant. And so relying on the cloud to scale up machines and turn on services at whim isn't always fast enough for us. And so right now we do everything on-prem.
That's good, thank you. And let me know if you need clarification on this one. Safim asks how you back up and restore a cluster.
So all of our cluster setup and install, it's really neat. Right now we've got, our cluster runs completely stateless. So we can reboot a node at any time and have it come up and rejoin the cluster. We don't save any state on hard drive except for caching Docker images. And so even that isn't really necessary. It's just faster that way. So we leverage SaltStack for managing our server configs and communication for changing those configs. So SaltStack holds the state for our nodes. We've got bootable images that they boot up off the network. And then of course, with the way that we've got our build pipeline set up, we can redeploy an exact production config within just a few minutes off using Helm and Codefresh.
And we didn't talk about that in this presentation, but we also have an operations Helm file that isn't fully fleshed out yet, but the objective is that all the things like Prometheus and you know, the non-business software would also be deployed with Homefile, so that the stuff running on Kubernetes we could start from scratch and have up in a matter of minutes.
Yeah.
Awesome. And on one of those notes, Mark asked, before the migration to Kubernetes, were you already working with Docker images?
No.
Yeah, we knew that we needed to do something, and there was a guy before me that was dabbling with a variety of things, hadn't gotten very far. I'd used Docker at a prior company, and its potential I thought was wonderful, but Docker's big weakness as a standalone product is in networking. So if you want to run Docker images on one machine, it does fantastic. But as soon as your problem scales to where it needs to go across multiple servers, Docker's solutions are really awkward. And Kubernetes with its networking solutions, various meshes and whatever, really handle that quite elegantly. So
you know, we did have to start using Docker before we got to Kubernetes. We needed to find a way to give the developers an environment that would be similar to what Kubernetes would deploy. And so we spent a lot of time learning how our company could use Docker and leverage those build environments, and then work that into our deployment pipeline for using those images.
And there was a significant effort to Dockerize our software that was running on those virtual machines. You know, the first image that we created was because the VMs were running CentOS 6, the image was based on CentOS 6. And after we installed all of those Python libraries and all of our application code and all of the RPMs that our application expected, it was a 1.5 gig image. not the ideal slim and trim Docker image, but it still gave us tremendous amount of flexibility and the ability to restart and monitor that we didn't have with the VM. So it was a good interim step.
All right, thank you, Ben and Jared. And we have a lot more questions rolling in. So we have about 5 more minutes for questions. So I'm just gonna keep on rolling. How do you collect logs of your applications running in containers? Do you log directly to ELK, or do you log directly to stdout, ERR, and then pick up by the cluster-wide log collector like FluentD? What is your experience and advice?
Yeah, so FluentD is what we use. It's really easy in the Kubernetes environment to just log to standard out and standard error. FluentD gets those and pipes those into our Upstack. So.
Sounds good, thank you. And let's see, Yafim has a follow-up from an earlier question. Say a data science team is requesting to deploy a new set of components. Did they need to manually go through each component to size the number of CPUs, amount of RAM, disk space needed for installation, temp space, data space, etc.? Or is there some automation to do pre-checks on the components against the provision system prior to the installation to ensure the deployment will not fail halfway? Did you get all that?
So a Kubernetes pod has two things that you can allocate. You can allocate CPU and memory. Disk space is going to be handled with outside of the pod itself, and is a separate question. But you can request a certain amount of CPU. You can request a certain amount of memory. And if the pod is created, then the pod is guaranteed the amount of CPU and memory that you've requested. There's also a limit that you can specify. And if the limit is higher than the request and there is additional capacity on the node that it is scheduled on, then you can use up to that amount. So for example, say that you requested 100 megabytes of RAM and a core of CPU, and then specified a limit of a gig of RAM and 2 cores of CPU. So if the memory is available on the node, it can use that additional memory. If it's not, then the pod would be killed and rescheduled. So to address your question, does somebody need to manually specify on each pod the amount of CPU and RAM? Yes. Setting those requests is really critical, because what Kubernetes is doing in the background is, say you have a bunch of different Kubernetes nodes, it knows how many pods are running on each of those nodes and how much of the RAM and CPU has been allocated. And so it goes and looks for a hole where it can stick that pod that it will fit. And if you don't specify the amount of CPU and RAM accurately, then the scheduler is going to break down and not work very effectively.
Yeah, I think too, though, to address the automation side of it, is it's totally, the whole environment is fully allows for you to try to automate that. We don't, but that is possible. You could fire up a test instance and run it through a sample workload and see what kind of memory and storage system requirements are, and then use that to build your Helm file charts and deploy. That's totally within the realm of the ability of all these tools. We don't leverage that today.
Yeah, we found in our situation that the production workload is so different than what we can generate in a test environment that we don't have a really good idea the first time we deploy something how much memory and CPU it's going to take. So our typical workflow is that we just give it a lot and then go and check and see how much it's actually using, and scale it back down from there.
And Yefim followed up. He said the point of his question was not to specify, but to leverage automation to deduce the requirements.
Yeah, and like Jared said, if you've got some kind of harness that you can put this in and deduce what those requirements are before, then yeah, you could absolutely specify them in advance and be accurate about it. We don't have that capacity yet.
Sounds good. And we are at the top of the hour, but we do have a couple more questions. If Ben and Jared, if you're game, and I'm just going to launch kind of our ending poll here. We appreciate everyone on the line. If you would answer these poll questions for us, and just a couple more questions, we'll try and get through them all. How do you organize your Helm charts for a multitude of microservices?
In general, we have one chart per deployment. There's a couple cases where a couple deployments are very tightly coupled, and it really makes sense to deploy those together. And in that case, one chart will deploy multiple deployments, but generally just one chart per deployment.
And those charts are generally kept in the same repo as the source code for that deployment. So everything is compartmentalized that way. And then in our Helm file definition, where we define what we want production to look like, that's where we pull in the image versions and things like that for those different deployments.
All right, and I'll make this our last question. When trying to adopt Kubernetes, do you find it useful slowly adopting it, moving to manual editing YAML files, then eventually getting to a more automated solution? Or looking back, would you try and jump straight into a solution you have now?
I don't know if that question is really answerable realistically, because some of the things that exist now didn't exist 2.5 years ago. And so, maybe hindsight's 2020. I think a gradual adoption is certainly a good thing, whatever tools you use, because there's just a learning curve. You'll make mistakes along the way, and learning and making mistakes on a small portion of your company's software is better than learning and making mistakes on the entirety of it. So I definitely recommend a gradual approach.
Yeah, the gradual approach is good. I think in regards to moving to, between manual editing YAML files and jumping straight to the solution, just because you use Helm charts doesn't mean you don't have to know what the Kubernetes YAML files look like. If you're going to tweak something in a deployment, or you want to set certain properties on that deployment, whether they're labels or annotations or command line flags for your container or something like that, you're going to need to know what those YAML files look like anyway. So I think getting familiar with those YAML files early on is really, really important. But I would suggest that as you're slowly adopting Kubernetes, move to Helm/Helm files as soon as possible. It'll save you a lot of time.
Yeah, you're going to want to have Minikube or K8s or micro K8s or something running on your laptop that you're deploying in, and yeah, absolutely use Helm from the start.
Excellent. Well, thank you so much, Ben and Jared, for reliving your past deployment pains with us and showing us how far you've come and how you've automated your deployments and saved a ton of time and made your deployments more reliable in the process as well. If you were where Vivint was in 2018 and you have more questions about how they adopted Helm, Homefile, Kubernetes, Codefresh, or Blue Matador, you can reply to my email tomorrow, which will have the recording in it and the slide deck, and we can help you answer your questions. So again, thank you so much to Ben and Jared from Vivint and Taylor and Trenton from Blue Matador for helping put on this webinar. And thank you for joining Codefresh Live. We will see you next time on Codefresh Live, and have a great rest of your day. Bye, everyone.